We're Calday Robotics.
Around the world, many areas struggle with a lack of access to healthcare equipment and qualified healthcare professionals.
According to the World Health Organization, cardiovascular disease is the leading cause of death globally.
With 3/4 of these deaths in low and middle income countries, where facilities to treat and diagnose these are severely lacking.
Our product can provide a cheaper, faster and more reliable method of diagnosing cardiovascular issues.
Especially in countries worldwide where equipment for diagnosis is not readily available.
Our device is a 3D printed digital stethoscope that records, displays, and processes heart data using AI. This will revolutionize the way heart data is monitored and analyzed.
Throughout this section, we've included lots of complex terminology, so feel free to search anything up. We've also included some helpful explanations and links on our GitHub repository.
Our integrated AI uses a deep convolutional neural network architecture to accurately and reliably diagnose heart irregularities such as murmurs and extrasystoles.
In order to make a prediction, the data is first converted into relevant factors, such as a zero crossing rate, a chroma short-time Fourier transform, a male frequency spectrum coefficient, and a male spectrogram.
This allows unnecessary information to be abstracted from the input data, while retaining relevant information for interpretation.
The data is then passed into a deep neural network that consists of 5 layers and over 95,000 trainable parameters.
The network consists of 3 one-dimensional convolution layers with ReLU activation functions and max pooling, and then 2 linear layers with ReLU and logarithmic softmax activation functions.
In order to train the model, we use the cross-entropy loss function as well as the AdamW optimizer with an aggressive weight decay to prevent overfitting.
Another step we took to prevent overfitting was to add dropout layers in between each convolutional layer.
We also upsampled the minority classes to prevent a class imbalance by creating synthetic data with added noise.
This allowed us to minimize loss and achieve an accuracy of over 98% on data that the model had never seen before.
Overall, it effectively assists medical personnel in one of the toughest aspects of medicine, diagnosis.
There is still much more accuracy that can be extracted from our model, but we experience limitations in terms of our dataset size.
Our digital stethoscope also has the major advantage of its low cost. This means our stethoscope can be much more accessible in areas where medical resources are constrained.
Overall, the commercial cost of the stethoscope is only £40.94. This is because we were able to source all of the external components for only £1.60.
Here you can see our cost breakdown based on the commercial viability of this product.
In order to achieve this, we used FDM 3D printing to create the sections of the stethoscope. The main head of the stethoscope is made out of PLA that can be easily manufactured in remote regions without the need for specialist fabrication tools.
Our product is also simple to assemble, with all of the 3D printed parts using a friction fit to hold them together. This means no glue or adhesives are required.
We decided to use the Raspberry Pi 3B Plus due to its sufficient computational power and relatively low cost.
We had many iterations of our head and ring to create a stethoscope that has the best audio output for further processing.
Here are all the iterations of our top ring, where we varied the material, shape, and internal diameter to optimize the tension of the diaphragm and contact area with the skin. This has allowed us to produce the highest audio quality possible.
One way that we found to reduce audio loss is using a TPU connection piece that applies pressure to both the stethoscope head and the microphone. This ensures that audio from the diaphragm reaches the microphone.
For the manufacturing, all the information can be found on GitHub, such as 3D models, sources to all components, a detailed build guide, and all of our code.
Here is the GUI for our digital stethoscope. It runs on the Raspberry Pi and can be connected to any monitor.
It shows a live pulse of heartbeats, contains input fields for the patient, and is able to use AI to output its diagnosis for heart conditions.
In order to calculate BPM, the Raspberry Pi uses a weighted decay function so it can provide a real-time output for doctors.
Our product enables efficient and reliable remote diagnosis to allow doctors to more easily monitor patients in remote areas.
It displays a digital representation of heartbeats for easy use by medical staff and accurate diagnosis for medical staff who may have less experience.
Ultimately, saving lives and allowing our product to improve healthcare accessibility globally.
Thanks for watching. We're Calday Robotics.